Good morning. Welcome to Lecture 8, the final in the series for Sociology 202 Online. Today our objective, we've really been building towards this for the duration of the semester, is measuring the association between variables that are measured at the ordinal and interval ratio level. So our objective today, we're going to learn about the ordinary least squares line, what some of you may have heard as the regression line. The topic today is bivariate regression and bivariate correlation, the final topics, as I said, for the course for this term, so that means we're getting really close. So congratulations to those of you that have made it through the course thus far. I can only expect that you're going to continue to do well through the last couple of problem sets and the final exam. So what I have up here on the board are 15 cases, n equals 15. And we have observations, actually two different sets of observations for those 15 cases. We have an occupational prestige score, which looks like in our data, it ranges from a low of about 14 points to a high of about 69 points. We have an occupational prestige score for all 15 members of our sample. And we also have the age of the members in our sample, which looks like it ranges from about a low of 19 to a high of about 67 years of age. So our objective here is to address the question, is there an association between a person's age, the independent variable, and a person's occupational prestige? So we're assuming that there's a an association between these two variables, and that what influences the other piece is that a person's age influences their occupational prestige. Going into this, my assumption would be that as a person increases in age, as the scores on the age variable increases, that we should see a positive association where the occupational prestige scores also increase in value. We'll see if that's the case or not. For each of these variables, we've taken all 15 cases and we've summed the scores. The sum of the 15 occupational prestige scores is 575. The sum of the age scores is 615. The remaining three columns are derived by taking pieces of the previous two columns. For example, column 3 is a y-squared column, where all we've simply done is take the observed occupational prestige scores in this first column and squared the values. For example, 32 squared is 1024, 50 squared is 2500. We've done that for all 15 occupational prestige scores, and we've summed those up. The sum of the occupational prestige squared scores is 25,695. We've also done the same thing for age. We've taken the observed scores for age. For example, 34 squared is 1156. 41 squared is 1681. Again, we've repeated this for all 15 scores. It's important when you do the computational math associated with these problems. If there are 15 cases, which is still a small data set, we're going to see that after a bit here, but you need to make sure, that you have the data for all 15 cases. So I like to count when I write these scores down. Just make sure you have 15 in each one of the columns. So the sum of h squared scores equals 29,731. And in the final column, all we have is simply a product. We take the observed age, for example, the observed occupational prestige score, 32 times the observed age, 34. That gives us 1088. 50 times 41 is 2050. We go through the process of multiplying each case's occupational prestige score times their age to give us a x times y, or in this case a y times x column. When we sum those scores, we get a summed value for y times x of 22,355. Now, this is the math associated with the problem, but really what our objective is we want to solve for this equation right here. And this equation starts out with a y, and it has a funky little hat over the top of it. This is statistical innovation in action. The official name of this symbol is y hat. It looks like it's a y with a little hat over top of it. And we get this value for every observed score in the distribution. We're going to get a predicted score. This is our ordinary least squares line, our regression line, and it's the most efficient line that can be drawn through a distribution of scores. It's the line where we're going to correctly predict the closest value for occupational prestige score when we know age using this equation. So we get this by taking A, which is the intercept. Some of you remember the idea of an intercept. It's the point where the regression line crosses the y-axis. Some of you learned this is that the intercept is the value for we would expect for y when x equals 0. I don't really like that interpretation unless it makes sense that x equals 0. For example, in this situation it wouldn't, that a person's age would be 0. We wouldn't be examining their occupational prestige score. So I like thinking about the y-intercept as the point or the score where the predicted values line crosses the y-axis. And then we have the slope, which some of you remember your geometric training, and you've learned that the slope is the indicator of the rise over run of the data, and that's absolutely true. In the ordinary least squares equation, the slope is the change in the independent variable that we would expect to see for a 1 unit change in the independent variable. Let me make sure that I said that. It's the change in the dependent variable that we would expect to see for a 1 unit change in the independent variable. So in this case, the slope would represent the change in occupational prestige scores that we would expect for every year older or younger the 15 members of our sample are. So again, the intercept, the point where the predicted values line crosses the y-axis, the ordinary least squares line or predicted values line crosses the y-axis. The slope is the amount of change in the dependent variable that we would expect to see for a 1 unit change in the independent variable. So every year older or younger our sample gets, we're going to expect that occupational prestige scores will change by a certain value. So our first objective, ultimately by the time we're done here today, we're going to accomplish a series of things. First of all, we're going to calculate the slope, then we're going to calculate the intercept, and we're going to script out the predicted values line for these data, and I'll talk about the interpretation of those. We are going to calculate the coefficient of correlation, what some of you have just simply heard about as the correlation score or Pearson's R. And we're also going to calculate what I think is the quan of all statistics, the coefficient of determination R squared, which in terms of the model approach to regression is the big thing. How much of the variation in the scores on the dependent variable can we account for or explain when we know the scores of the independent variable? And that's the basic essence of regression. So what I'm going to start out here with today is I'm going to erase all of this hard work, scripting up all of the data that I put up on the board. I wanted you to see this because we're going to start out with some formulas that are going to ask us for specific things in terms of the sums of the scores that we have up here on the board. So let me get this board cleaned up just a little bit. And what our first task is we're going to solve for the slope. And according to our formulas at the end of the chapter in Joe Healy's book, we get the slope by taking n, which our observed n is 15 cases, times the sum of xy, minus the sum of x times the sum of y. We're going to divide that by n times the sum of x squared minus the sum of x squared. And you'll notice that particularly in the denominator of this formula, we're not accounting for any of the values for y. We're really trying to get an estimate for the value of x, indicating the amount of change in our dependent variable that we would expect for a 1 unit change in the independent variable. So let's go ahead and change out these symbols for actual data. We know that in our data set we're working with 15 cases. According to our estimates, the sum of xy is 22,355. We know that the sum of x, which was the sum of our age scores, is 615. Because we're going to multiply, I'm going to put brackets in mine. The sum of the occupational prestige scores, 575. We're going to divide this by, again, 15 as our sample size. The sum of x squared, we got 29,731. Minus the sum of x, and this is the big thing, right? This is the sum of x squared. We had an x squared column. This is simply the sum of those scores. This is asking us to take the sum of x, which we already know is 615, and it's saying we want to square that score. So that's one of the big initial things to keep in mind, that there is a difference between the sum of x squared. We have an x squared column. It's simply the sum of those. In this data, the value is 29,731, and the sum of x squared, which is simply just taking the x squared scores, or excuse me, the sum of x scores, and squaring those values, which we have determined that those are 615. So I'm going to identify that the highest order of operation in the formula is the exponent, and I'm going to go ahead and start there. But because the math is computationally quite a few steps, I'm going to take each of the pieces and parts of this in order. I know that please excuse my dear Aunt Sally rubric that we've been following. We should start with the exponent. So I'm going to go ahead and do that. 615 squared gives us 378,000. 225. If we take 15 times 29,731, we get a score of 445,965. On the top, 15 times 22,355 gives us an estimate of 335,325 minus the sum of x squared, excuse me, the sum of x times the sum of y. 615 times 575 is 353,625. Alright, so we've made it through the first stage of this. We've taken n times the sum of xy. We're going to subtract that from the sum of x times the sum of y. We're dividing that by n times the sum of x squared minus the sum of x squared. So in this next step, we simply subtract. If we take 353,625 and we subtract that from 335,325, we get a negative number, 18,300. And I want to pause there. We know in division, whenever you divide a positive number by a negative number, or a negative number by a positive number, just like multiplying, the resulting number is negative. So this is the first check balance here. I expected that I had said I thought that the association between age and occupational prestige should be positive. That as the members in our sample get older, their occupational prestige scores increase in value. We're already realizing that that's not correct. Our slope is going to be negative, which means as our members in our sample become older, the predicted score for their occupational prestige score is going to go lower in value. So in our sample, the older you are, the lower your occupational prestige score. In the denominator, we're going to subtract 378,000 from 225. Or excuse me, we're going to subtract 378,225 from 445,965. we're going to get a difference of 67,740. And I should have waited there. Obviously, if we would have gotten both negative numbers, that would have changed the direction of our slope. So in the last step, we simply divide negative 18,300 by 67,740, and what we get is a value for the slope of negative 0.27. Right, negative 0.27, which is suggesting that there's a negative relationship between age and occupational prestige. So earlier I had talked about kind of the generic interpretation of the slope being the slope represents the amount of change in the dependent variable that we would expect to see for a 1 unit change in the independent variable, but we now have a score. And we know that for every age older members in our sample get, we expect their occupational prestige score will go down by negative 0.27 units. All right? So thinking about it, a person that's 10 years older than somebody else, we would expect their occupational prestige score to be approximately 2.7 points lower than the younger person. All right, again, our objective, we want to be able to solve the predicted values equation, or at least have numbers that we can put in and replace of the symbols. We have the slope. That's the first major task. The second major task is we want to calculate the intercept, which equals A, and you'll see here why we needed to have A. Because the equation for the slope is we take the average score for y minus the slope times the average score for x. Again, y bar, x bar, the average for y, the average for x. We actually haven't calculated these scores yet, so let's go ahead and do that. To get the average score for y, we're going to take the sum of y, 575, divide that by 15. We're going to get an average score of 38.33. The sum of x, we're going to take 615, divided by 15. And we're going to get an average score for x of 41. Now we can solve for the intercept. We know the average score for y is 38.33. Minus, we know the slope, negative 0.27. And the value for y is 41. Continuing on, 38.33. We take negative 0.27 times 41. We get an estimate of negative 11.7. It's looking a little bit like a 9. In the final step, we take negative 11.07 and we subtract that from 38.33. And we know when we subtract a negative number from a positive number, it's like adding two positive numbers. So we're going to get a value of the y-intercept based on the data examining occupational prestige and age of 49.4. So the y-intercept equals 49.4, and we can script out now the predicted values equation, which is y hat equals 49.40 plus our observed slope, which is negative 0.27 times x, and I'm putting the sub I in there. So the important thing for this is that for every observed value of x, we had 15 of those. We could simply plug in the observed value of x for each case times the slope of x. We would then add that to the y-intercept and for all 15 observed values in our data set, we could get a predicted value of y. We're not going to do that. I'm not going to ask you to do that either here or in the problem sets or on the final exam, but I want to let you know that if we wanted to, we could add another column of scores to that column that we set up, and that would be the predicted value of y. We now have the mechanism whereby for every observed value of x, we could get a predicted value of y. And it's important to think about that because what we could do with those predicted values of y is we could create a scatter plot looking at the actual co-occurrence of x and y, and you would see that this line, y hat equals a plus b times x sub I, it's a straight line, and it would put a line through the observed distribution of scores that minimizes the difference between the actual value of y and the predicted value of y further than any other equation that we could imagine mathematically. It's the best linear, unbiased estimate. So we've been successful in, up to this point, calculating the slope and calculating the intercept. What we want to turn to now are really the two primary measures of association. First, the coefficient of correlation. We're using an equation based on Pearson's R, and you're going to see that it gives us the equation gives us something that we've seen before plus something that we haven't. The numerator, we've seen this part of the equation before, n times the sum of x sub I minus the sum of x times the sum of y. That part of the equation is the same equation that we used for the slope. We already know that this value is negative 18,300. In the denominator, this is the important part. We're going to take the square root of the entire denominator. And this is the most consequential piece of this estimate. If you're going to make an error in the calculation of the coefficient of correlation, it's most likely that you forget to take the square root as part of the estimate. The first piece, there are two pieces of this estimate. They're both in boxes, which means that eventually we're going to multiply those. The first piece of this we've already seen as well. So I'm going to go ahead and put the boxes over here. We've already calculated n times the sum of x squared minus the sum of x squared. If we just look at the numerator, which we know the value is negative 18,300, times just this piece of the denominator, which we calculated before as 67,740. If all we had were these two numbers, we divide those and get negative 0.27, which is our slope. But what's different between the slope and the coefficient of correlation is that in the denominator of the slope, all we accounted for were the values of x. But in the correlation score, we're looking at the relationship between x and y. So we're also in the denominator going to account for the scores for y. We're going to do the same thing. We're going to take n times the sum of y squared minus the sum of y squared. So this is the piece that I'm going to work on over here. We know that our sample size is 15 cases. The sum of y squared, 25,695. According to our formula, we're going to subtract that from the sum of y, which is 575 squared. All right, so we'll start out with 575 squared. Gives us a score of 330,625. 15 times 25,695 gives us a score of 385,425. Fix this. our second piece of the estimate here, when we take 330,625 and subtract that from 385,425, the difference is 54,800. All right, I'm going to clean this up just a little bit. We know our numerator, negative 18,300. We know that we need to keep the square root here. And multiply the boxes together, 67,740 times 54,800 gives us a score under the square root of 371,215, and then 3 zeros. 371,215,2000, which if we're thinking about the score, there's 3, there's 3, there's 3. 3,712,152,000. In the next step, we're going to take the square root. Remember, the most common computational error is failing to take the square root after you've solved for the covariation as it is between x and y. The square root of 3,712,152,000 is 60,927 out to the second decimal place, 0.43. We subtract those and we get a coefficient of correlation score of negative 0.30. And this is a good check and balance to keep in mind. We have already determined that the slope, assessing the relationship between occupational prestige and age, is negative. We determined previously that the slope was negative 0.27. The sign of the association between the slope and the coefficient of correlation should be the same as they are here. So what is the coefficient of correlation? The generic answer is that the coefficient of correlation examines the relationship between two variables. There are kind of three pieces of information that are given in the coefficient of correlation. First, if the correlation score is 0, it means that there's no association. If the score is not 0, it means that there is. So the first piece of information is if there's a score that's non-zero, it means that there's at least some association between the two variables. It also tells us the direction of the association. If the score is negative, it means that as the scores on the independent variable go up, the scores on the dependent variable go down, which is the case here. As members of our sample become older in age, their occupational prestige scores decrease in value. And then finally, we can look at the size of the association, and an observed correlation score that is 0.01 to 0.29, we would classify that as a weak relationship or a weak association. An association between 0.30 and 0.69, a moderate association, and anything that's 0.70 to 0.99 as a strong association between the variables. It's unlikely, but if we ever got a perfect association, a score of 1, it means that there's exact parallel between the change in x and the change in y. I don't know that I've ever seen two variables correlated at 0.10. Most times they tend to be variables that are entered into a data set twice. Any variable's correlation with itself is going to be 1. In the last stage of this, we're going to convert the coefficient of correlation score into the coefficient of determination score, and symbolically we're taking r, the coefficient of correlation, and we're converting it into r squared, the coefficient of determination, and it's as simple as taking the observed correlation score and squaring the score. So if we take negative 0.30 and we square that, negative times a negative becomes a positive. Whenever you multiply a proportion, the resulting sum is going to be smaller than what you started with. Based on the observed data, we get an R-squared score of 0.09. The R-squared score tells us the following. The R-squared score tells us of the variation in the scores on the dependent variable, the distribution of occupational prestige scores, how much of that variation can we account for or explain when all we know are the scores on the independent variable. In this case, the independent variable is age, and the R-squared score tells us that when we know a person's age, we can account for or explain 9% of the variation in occupational prestige scores. In the next series of this, we'll take a look at this coefficient of correlation score, and we'll take to task the question, is the observed correlation statistically significant? I'll look forward to that, and we'll go from there. I'll see you next time. Thank you very much.